Okay, here is another question based on the principle of moments. A child P of mass 20 kilogram is playing on a uniform plank of 2 meters length resting on two supports loosely as shown. Okay, so we have a rod here. The rod has a mass of, the rod has a length of 2 meters, and then what? You know, it is being supported here on two wedges. Okay, and this distance they have given, it is 25 centimeters, and this is also 25 centimeters. A child P of mass 20 kilograms is playing on a uniform plank of 2 meters length. So this is 25, this is 25, no, this is not 25, it is 50, it is 50 centimeters in the question. This is also 50 centimeters, okay? The extended portions are 50 centimeters each. And then what? The total length of the rod is 2 meters, which would make what? This is 50 centimeters, altogether it is 1 meter. Then this distance must be equal to 1 meter. Right. And then what? A child is playing on this. A child starts running from this end and she is coming over here, okay? And then she can reach a minimum distance of 25 centimeters from the edge of the plank without toppling it over the support. Okay, find the mass of the plank. So she starts running from here and she can come up to this point. Which point? The middle of the section now. They say that this distance is, the distance up to which she can come is 25 centimeters from this wedge. So right now she is standing over here, right? Standing over here. Till that point she can come in. If she goes beyond this, this rod will be coming off from the wedge. Understand? So it is kept like this. And she is coming from this side, like this, like this, like this, like this. Till this point she can come comfortably, right? If she goes beyond this, automatically, you know, it will come off from the wedge like this. Okay, so let us draw the normal reactions now. The normal reaction is R1 here. The normal reaction on this wedge is right, R1. And the normal reaction here is R2. So there are two normal reactions at the two wedges. And then weight is acting where? Weight is acting through the center of mass. Weight is acting through the center of mass of the rod, right in the middle. The weight is mg. Weight is mg. Okay. And weight of this gird, weight of the gird is like 200 Newton. Why? Because mass of the gird is 20. So 20 into 10 is 200. So we got a system like this. So let us write down a couple of equations, then that's the end of it. Right. So the rod is balanced on two wedges, supported on two wedges, extended portions of 50 centimeter, and then the weight is acting through the middle, like middle of the rod. Weight is acting through the middle of the rod, and then what? We have two normal reactions. One here R1, another normal reaction R2. And she is coming from this side, she comes to this point, and then if she goes beyond that is a critical point. She goes beyond that, this will come off from the wedge. Okay, this will come off from the wedge. This is the wedge. Okay, so let us write down an equation for the translational equilibrium. So what do we write? I call this by the name W, wait. So if you write down the translational equilibrium, equation for translational equilibrium, R1 plus R2 should be equal to 200 plus W. Okay, I'll tell you why. Because if we have equilibrium, translational equilibrium, that means forces in y direction should balance each other. What are the forces in the upward direction? One force is R1, another force is R2. So the total force in the upward direction is R1 plus R2. What is the total force in the downward direction? One force is 200, the weight of this gird. Another force is W acting through the center of mass, weight of this rod. So I got my first equation now. Let us put it as equation number 1. Now this is obtained by taking what? Translational equilibrium. Condition for translational equilibrium is sigma f should be equal to 0. Sigma f should be equal to 0. Now let us look at rotational equilibrium. Sigma tau should be equal to 0. That means moments about a point must be equal to 0. All are creating moments here, I'm going to find the net moment about this point, about center of mass of the system, right? So there are, this guy is creating a moment, torque. This is creating a torque. This is creating a torque. While this force won't create a torque. Why? This force is acting through the point about which the torque is calculated. Okay? Look at that. Where I'm going to calculate the net torque on the system. I'm going to equate that to 0 now. Now, I won't consider the torque due to weight here because we are going to find out what? The torque about the center of mass. Torque with this point as point of rotation. This is the point about which you are finding the torques. So I'm going to write the torque about this. Torque by this force, weight. So what is this? The weight is 200 into the distance. Distance is what? This is quarter of a meter now. This is half meter, but they say she is at 25 centimeters. Then this must be 25 now. And this is 50. This is 50 centimeters. This is 25 centimeters, right? She is standing in the middle of this extended section now. So 25 centimeters and 50 centimeters, 75 centimeters. That is 3 by 4. Right. And then torque by this force R1, normal reaction. How do we take it? I can take it R1 into, what is the perpendicular distance? Perpendicular distance is this distance, no? We are finding, remember, we are finding torque about this point. This distance is what? 50 centimeters. 50 centimeters is half meter, right? Then, the last one, I am finding the torque given by this force, this normal reaction. What about that one? R2 multiplied by, the distance there is what? About the point of rotation it is 50 centimeters. This distance is also 50 centimeters because weight is acting through the middle of the rod. Correct? So, that is also 50 centimeters, which is half. I want the net torque to be equal to 0. Why? Since we have rotational equilibrium here, right? Rotational equilibrium here. And then, think about this. This is creating an anti-clockwise torque. Look at that, look at that. If I keep it here and if I pull it downwards, it is creating anti-clockwise torque. This is creating an anti-clockwise torque. Anti-clockwise torque is put positive. Then what about this one? This one, this is creating, this R1 is creating a clockwise torque. If I hold it here and if I pull it up from this side, it is creating a clockwise torque. So, clockwise torque is negative. Then how about this one? I am holding it here, then I am pulling it up here. Now, it is creating anti-clockwise torque again. So, that's again positive, right? So, let us simplify this. This and this are gone, it is 50. So, 150. 50 into 3 is 150. Minus R1 by 2 plus R2 by 2 is equal to 0. Correct? So, I'll take this to right hand side. This to right hand side. What do we get? Both common 2 there now. So, R2 goes to the right side. R1 goes to the right side to become plus R1. R2 goes to the right side to become minus R2 divided by 2. Both these terms have 2 denominator now. And the other side is 150. So, what we have now? So, let us cross multiply. R1 minus R2 should be equal to 2 into 150, 300. That is my equation number 2. So, I got 2 equations now. Now, before doing that, let us put the critical condition now. She starts walking from this point. Okay? She keeps walking like this, like this, like this, like this, like this, like this, like this. And she reaches to this point. And if she crosses beyond this point, what happens? This will come off, right? When it comes off, the normal reaction becomes what? 0. So, the critical condition is normal reaction on the second wedge should be equal to 0. Normal reaction at the position of the second wedge should be equal to 0. Because just beyond this point, if she goes just beyond this point, this is going to come off anyway, right? So, as a critical condition, you can put the normal reaction on this to be equal to 0. That is the most important point here, right? If you put R2 equal to 0, it's done, right? Tell me what R1 minus R2 is made 0 here. I told you the condition here is that the rod should not be coming off. It is same as the rod should be coming off, right? The condition at which the rod is coming off from the wedge. So, R1 minus 0 is equal to 300. That makes it R1 is equal to 300 Newton. So, I got a normal reaction at the point of first wedge. I can put it straight away to this, right? So R1 is 300. So let us write equation number 1 becomes what now? I'm writing it here. 300. Equation number 1, 300 plus R2 is 0 should be equal to 200 plus W. So I take it left hand side. 300 minus 200 is equal to W. That is 100 is equal to W. W is 100 means mg is 100. Okay, weight is mg, no? I can cut g. G is 10, no? 10 with the 10. So what we get now? Mass of the rod, mass of the plank is 10 kilogram. Final answer is 10 kilogram. It's a reader question. It's an important one. Okay, so it's easy. We have the rod here. We take two conditions. In such question, we take two conditions. One is the condition for translational equilibrium. That means the rod is not moving up. It is not moving down either. Right? So which means what? The net force on it is 0. Net force is what? On this bed, the normal reaction is R1. Here it is R2. Both the normal reactions, R1 plus R2, should be balancing the weight of this rod plus weight of the girl. So W plus 200. 20 kilogram is the mass. Then weight is 200. Then you put the second condition. Torque is equal to 0. Because it is also a rotational equilibrium, right? As long as she stays within the point, not within the distance, right? So I'm writing down all the torques. Torque due to the weight of this girl, torque due to this normal reaction, torque due to this normal reaction. I won't take the torque due to this weight. Why? Because the torque about this point is to be calculated. So torque, since the point is same as the point about which the torque is to be calculated, that is 0. That torque will be equal to 0. So I can write down the torque due to this, force into perpendicular distance, force into perpendicular distance, force into perpendicular distance. And then give the signs whether, as per the direction. No? If it is anti-clockwise, put it as positive. Clockwise, it is negative. Solve it. You get another equation. R1 minus R2 is equal to 300. And for the critical condition of the rod coming off from the wedge, you should put what? If it is coming off, this normal reaction, it loses contact. That means normal reaction would be equal to 0. So you put that condition over here. R2 equal to 0. You get what? R1. Normal reaction on the first surface you get as 300. Put it back here. In this equation, solve it, you are getting weight is equal to 100, that is mg is equal to 100, or m is equal to 10 kilogram. Mass of the rod is 10 kilogram. Okay.